Every living thing, from a tiny bacterium all the way up to you and me, is made of cells. But have you ever stopped to think about what actually defines a cell? What separates all that intricate, organized machinery inside from the, well, chaos of the outside world? It all comes down to an incredibly thin, super flexible, and unbelievably important boundary, the plasma membrane. So today, let's dive in and get to know this dynamic gatekeeper.
All right, here's our game plan. We're going to start with the big picture, looking at the membrane as the cell's essential barrier. Then we'll zoom in on its foundation, which is all about lipids. After that, we'll meet the proteins, the real power players that get all the work done. We'll see how it all comes together in what's called a fluid dynamic mosaic. And then we'll wrap up by understanding why this very specific structure is just so critical for life.
So let's just kick things off with that fundamental question. At the most basic level, what is that line in the sand between life and non-life? Well, the answer is this amazing structure that we're about to break down. Okay, first up, the cell's essential barrier. This is that unbelievably thin line that makes everything we call life inside a cell even possible.
So just how thin are we talking? Get this, it's only about 7 to 8 nanometers thick. Now, to put that into perspective for you, a single sheet of paper is about 100,000 nanometers thick. So this barrier is literally thousands of times thinner than paper, and yet it's strong enough and smart enough to protect everything inside. It's kind of mind-blowing. And look, this isn't just some abstract concept. It is a real physical thing. What you're looking at right here is an actual image from an electron microscope. See those two thin, dark lines? Those are the plasma membranes of two different cells pressed up against each other. That delicate little boundary is everything. It's all that separates the ordered world inside each cell from the space between them. But don't let its size fool you, because this membrane has some huge responsibilities. First, it acts as a selective barrier, kind of like a club bouncer, deciding what can and can't get through. It also actively manages the shipping and receiving of specific molecules. And maybe most importantly, it's the cell's communication hub. It picks up signals from the outside world and relays those messages to the inside. So yeah, it's the border patrol, the post office, and the cell tower all rolled into one. So the big question is, how do you even build something like this? How can it be so thin but so effective? Well, to figure that out, we gotta zoom in another level and look at its foundation. Turns out, the secret sauce is a very special kind of fat. And here is the star of the show, the phospholipid. Now, just look at its structure. You can see it's got two really distinct parts, this round head at the top, and then these two tails just hanging down. This simple two-part design, well, that's the key to the whole thing. Now, there's a fancy scientific term for this property, amphiphilic. It's a bit of a mouthful, I know, but all it really means is that this molecule has a split personality when it comes to water. That polar head is hydrophilic. Hydro for water, philic for loving, so it loves water. But the nonpolar tails, they're hydrophobic, phobic for fearing. They hate water and will do pretty much anything to get away from it. So, what do you think happens when you dump millions of these little guys into water, which is basically what the inside and outside of a cell is? Well, something amazing happens. They assemble themselves, automatically. The water-loving heads all turn to face the water on the outside and the inside, while all the water-fearing tails tuck themselves away in the middle, safe and dry. And just like that, you get a stable, two-layered sheet, the famous lipid bilayer. No instruction manual needed. But the phospholipids aren't totally on their own. They've got a couple of important sidekicks. You have cholesterol molecules that wedge themselves in between the phospholipids. They're like little structural supports that keep the membrane from being too flimsy. Then, on the outer surface, you've got these things called glycolipids. You can think of them as little ID tags that help cells recognize each other, which is super important. Okay, so we've built our basic wall. But a wall's kind of useless if you can't have doors or windows. And that brings us to the real action heroes of the membrane, the protein power players. These are the specialists that are embedded in that lipid wall, and they're the ones that get all the important jobs done. This diagram gives you a really great sense of it. You can see all these different proteins hanging out in and around the membrane. Some of them, the big integral proteins, go right through the entire thing. Then you've got others, the peripheral proteins, that are just kind of stuck to the surface on one side or the other. And some have these little sugary chains attached, making them glycoproteins. So really, the key difference is where they live. Integral proteins are true residents of the membrane. They are embedded deep inside it. Peripheral proteins, on the other hand, are more like visitors. They're loosely attached, maybe to deliver a message or to carry something, and then they can leave.
And what do these proteins actually do? Oh, just about everything. They give the cell structure, they act as enzymes to speed up reactions, they work as markers for recognition, and here's the big one. They form all the channels, pumps, and receptors that let the cell interact with the world. So if the lipids are the walls of the house, these proteins are all the doors, windows, and the entire electrical system.
So now it is time to zoom back out and put all of these pieces together, because you might be getting the impression that this is a rigid, static wall. The reality is so much cooler. It's actually a fluid, dynamic mosaic. This whole concept actually has a name, and it's a perfect one: the fluid mosaic model. It was developed by two scientists, Singer and Nicholson, and the name itself tells you the two most important things you need to know. It's fluid, meaning it moves, and it's a mosaic, meaning it's made up of lots of different little pieces.
And this image right here shows the whole idea perfectly. Think of the membrane as this two-dimensional sea of phospholipids, and floating around in that sea are these big protein icebergs, the channels, the pumps, the receptors. Everything is just kind of bobbing along. Crucially, none of it is locked in place. All these components can just drift around laterally, constantly shifting and changing.
So just how fluid is this sea? Well, it depends. A few things can change it. Just like butter, if you raise the temperature, the membrane gets more fluid, more runny. Cholesterol, as we said, actually acts like a stiffener. It adds rigidity. Even the type of lipid tails matters. And if you pack in a ton of proteins, it's like a traffic jam. Things get more crowded and less fluid.
And that brings us to our final and honestly our most important section. Why does any of this matter? Why is it so important that the membrane is a fluid mosaic? How does this specific design actually make life possible?
Here's the number one thing to take away. The membrane's fluidity isn't a bug, it's a feature. In fact, it's the feature. The cell needs it to be fluid. This is what allows proteins to move around, to come together to carry out a task, and then to move apart again. It's what lets the cell change its shape, absorb things, spit things out, and talk to its neighbors. A solid, rigid wall just couldn't do any of it.
So ultimately, you should stop thinking of the plasma membrane as just a simple container. It's not a bag. It is a highly sophisticated, incredibly active interface with the world. It's a complex machine designed for one main purpose: to sense what's going on outside and to pass that information inside so the cell can respond, adapt, and, survive.
And that leaves us with one final thought to chew on. We've seen that the incredible, beautiful order of a living cell is separated from the total chaos of the outside world by nothing more than this flimsy, shifting, fluid barrier that's just a few molecules thick. So if that's the line, if that tiny fluid barrier is all there is, what does that tell us about the delicate, dynamic, and truly amazing nature of life itself?